Thank you for joining us. My name is Vijay Prasad, and I am a fourth-year computer engineer. I will be joined later by my colleagues Juan Elizondo Villasis, a third-year electrical engineer, and Siddhanta Panda, a second-year computer engineer. Together, we will discuss our work with spectral optimization using the discrete prolate spheroidal sequences. First, we must understand that classical signal processing has centered around the Fourier analysis, which has introduced a mathematical paradox: the idea that a signal cannot have finite support in both time and frequency domains simultaneously. This idea begs the question: to what extent can a band-limited signal also be time-limited? Here, we show the first four discrete prolate spheroidal sequences, or Slepian sequences. These sequences provide an efficient representation for discrete time signals with maximal spectral concentration in a given frequency interval, say minus omega to omega. In other words, the first Slepian sequence, plotted in blue, seeks to maximize the energy contained in the band of minus omega to omega, with each subsequent sequence orthogonal to the previous. Using the Slepian sequences, we seek to explore signal processing applications typically approached using Fourier analysis. First, we explore beamforming, a technique that uses sensor arrays for spatial filtering. Next, we develop sleptograms, which provide a visual display of a frequency spectrum. These sleptograms are comparable to spectrograms as computed by the short-time Fourier transform. Siddhanta will now discuss beamforming.
We will start with discussing how we use the Slepian basis in spatial filtering. So we attempted to create a MATLAB simulation of a 64-element phase array antenna as a detector. We simulated signals coming from different directions by creating sinusoidal modulation vectors that fire 5 beams from 5 different incident angles. The signals that we received from these sinusoidal modulation vectors were then projected separately onto the Slepian basis and the Fourier basis to make a comparison. It was observed that the principal beam in the case of the Slepian basis was much wider than the principal beam in the Fourier basis and also had significantly lower side lobes. This enabled a much better isolation of the sources using the Slepian basis compared to the Fourier basis. Out of the 5 different incident angles, we are showing the power spectrum plots using the Fourier and the Slepian basis centered at 30 degrees. We attempt to show how the Slepian basis can efficiently be used to isolate the different sources radiating information along different directions. We are using 30 degrees as an example. We can see that in the case of the Fourier basis, we have a principal beam at 30 degrees and we have extremely high side lobes, which implies that the Fourier basis is not able to uniquely pick up information coming along the 30-degree angle. On the other hand, if you look at the Slepian sequence being used as the basis, we can see that the principal beam at 30 degrees is wider than the Fourier basis, the Fourier beam, and we have significantly lower side lobes, thereby showing that the Slepian sequence is able to uniquely pick up information coming along the 30-degree angle and will suppress information that is spread across the other angles. The efficiency of a system conducting array-based spatial filtering is measured by its ability to isolate sources or pick up information along specific directions. The Slepian sequence, with its significantly lowered side lobes, demonstrate the fact that it is a much efficient system that addresses this problem of array-based spatial filtering encountered using the Fourier basis. In this slide, we again attempt to draw a contrast between the power spectra using the Fourier and the Slepian basis of increased dimensions. We can observe improved behavior in isolating the incident modulation vector along the 30-degree angle. In the case of the Slepian basis, we can see a much wider principal beam and significantly lower side lobes. In the case of the Fourier basis on the left, we can see a very thin principal beam and lower side lobes. We can see that improvements in the Slepian beam is consistent with increasing the dimensions of the Slepian space. As in the previous case, we used a 1 dpss, and over here we are using 5 dpss as the basis for our projection matrix. As far as the target for array-based spatial filtering goes, we can see that any system that implements the Slepian sequence shows promising behavior of isolating information from a specific source at a specific angle from the detector.
Another way in which we can compare the Fourier transform and the Slepian transform is through spectrograms and leptograms. A spectrogram shows the power of a signal versus time in the frequency spectrum using the Fourier transform. A leptogram does the same, but with the Slepian basis. In this case, we are looking at a time slice of 3 of these images. The signal of interest is a sum of 1,000 sinusoids with frequencies varying around 2.8 kHz. Here we can see that the leptogram beam, the red line, is a bit wider than the spectrogram, the yellow line, but it also has significantly reduced side lobes. The blue line is a multi-tapered version of a leptogram. This uses the first 2 and W Slepian basis vectors to estimate the power spectrum of a signal, where N is the signal length in this time slice, and W is the bandwidth. This raises the side lobes above the spectrogram side lobes, but it also filters out the captured noise in the signal. Now let's take a closer look at these differences in the spectrogram and multi-taper leptogram. The figure in the right shows a noisy audio recording of Pachelbel's Anonymity. The spectrogram shows the content in octave 5, which has a frequency range of about 500 to 1050 Hz. Notice that the captured power range is of about 80 decibels, and that there are several instances of notes appearing with power leaking into neighboring bands. If we take a look at the multi-taper leptogram, we see that the captured power range was reduced to about 55 decibels, and that the frequency bands for the notes has become larger. However, the bands have sharper drop-offs than before, and looking at the start of the recording, we can really appreciate the smoothing effect of multi-tapering. Where before we had random spikes in the frequency bands, we now see a relatively smooth spectrum.
We have demonstrated through examples of beamforming and spectral analysis the efficiency of the Slepian sequences as compared with the Fourier basis. Future OR students may seek to apply Slepian analysis to feature extraction and possibly dimensionality reduction techniques. We thank our faculty advisor, Dr. Justin Romberg, for sponsoring our work, and Mr. Coleman DeLude for his guidance and mentorship throughout our project. Thank you for your time.